Good morning. We have been discussing about metal working deformation processing. Last class we primarily looked at the uh, effect of pressure or load that you apply on a material and how does the resultant deformation take place. And you will see that always metal deforms with the application of stress, but there is no change in volume. Now, in most processes you will find dimension in one or two directions, they change at the expense of others. For example, in this particular case, if you apply compressive stress like this, in that case its thickness will decrease and it will increase in this particular direction. There is an increase in length along this direction, there is a decrease in thickness along this direction, and we say that amount of deformation or plastic deformation is represented as ln thickness T over T naught. This is the true plastic strain. This is the thickness at any point and this is the initial thickness. Now, in this particular case, if other side it is not in a die, then in one side, this side there is a reduction in thickness and on the other two side it expands. But often we do this forging is done in a die where the elongation in one direction is restricted. In that case, it is a situation of plane strain compression, and likewise rolling is also a situation of plane strain condition, where you have two rolls rotating at a constant speed and you have the job which goes through this, and the thickness, this is the T 0 and this is the final thickness. And in this case, the elongation this side, that means the material, the job elongates at the expense of its thickness, but the volume remains constant. Now, let us now see that this type of processing often can be done either at a room temperature or low temperature or at high temperature. If it is done at high temperature, we usually call it rolling at a hot working, and if it is done at a low temperature, we call it cold working. And we looked at some of the structural structures that devolves as a result of both cold and hot working, and we have seen that this temperature, concept of temperature to decide whether it is hot or cold work is relative. It scales with the melting point, this is T m is the melting point, but it is in degree Kelvin, degree absolute. So, if it is done below half its melting point, then it is cold work. If the working is done above 0.5 T m, then it is hot work. Therefore, lead if you are forming at room temperature, it is hot working, but steel if you are working rolling at room temperature, it is cold working. And obviously, there are few other points that comes up. We know that strength of a material decreases as you increase its temperature. Therefore, hot working, the load that you need to deform the material will be very low, whereas in case of cold working, the amount of that load, since it increases, so amount of deformation that you can give is very low and the load on the rolling mill will be very high. So, this is what is listed here. It needs the rolling load will be high, or deformation forging press you need a higher capacity press, whereas for hot working a low capacity press. But there is an advantage of cold work, because cold work there is no interaction with environment is more or less inert, whereas in case of a hot working you have to often depending on the material you may have to offer some kind of protection, or else there will be scaling loss. So, some of the metal will oxidize and it will, the loss will be relatively high in case of hot working. Now, the cold work material you will find the grains are elongated, which shows sign of deformation, whereas hot work something happens during the process of working, the material grains deform, but the grains they recrystallize or they change, I mean new grains are also nucleated and they grow, and these grains are equiaxed, whereas here these are elongated. Because of this type of nature, elongated grain, the cold work material has a texture, has a preferred crystallographic arrangement or alignment of grains. So, this makes the property of a cold work material anisotropic, it depends on the direction, whereas hot work material there is every chance that your property of the material will be isotropic, it will be independent of the direction. Now, strength of the cold work material, because it hardens, the strength will be higher, whereas strength of hot work material will be relatively low. It will be something similar to normalized structure or annealed structure of the metal. Now, ductility in case of a cold work material will be poor, ductility of a hot work material will be high, and other physical properties also will change, like conductivity will be poor. Here hot working, the conductivity will be good. Likewise, there will be several other physical properties that also will change. For example, density. See, if when you deform a material as a cold working, you generate lot of dislocations, and we know the edge dislocation is made up of extra half plane, and beneath the plane there is a vacant lattice, I mean a vacant plane, lots of vacancies are there. So, one obvious things that comes up, that there will be certain other changes that will take place because of the presence of dislocation. There will be lot of stored elastic energy. The density of the material of a cold work material may also may be slightly less than annealed material because of high vacancy concentration, high dislocation density. Now, so effect of cold working, which is listed here, there is a change in grain size, shape, there is a development of texture, and the dislocation density increases. So, there will be stored energy will be very significantly higher in cold work material, and we know that energy of a dislocation is 0.5 g. G is the shear modulus, B is the Berger vector square. Now, each dislocation has this much of elastic stored energy. Now, imagine as a result of cold working, dislocation density can increase from 10 to the power maybe 10 to 10 to the power 16 number of dislocations per unit area per meter square. So, imagine how much will be if you can substitute this here. So, that means you multiply by the dislocation density. So, this will be the stored energy in a cold work material, and this will be substantially high. And the material work hardens, there will be loss of ductility, there will be increase in strength, and there is an increase in residual stress. So, the different area of the material may deform to different extent. So, there will be some elastic stored energy because of the mismatch of this elastic strains, and then there will be stored energy as a result of high dislocation density, but the crystal structure of the material that will remain unaltered. The crystal there may be because of lattice residual stresses, lattice parameter may change slightly, or that lattice parameter change, and there may be wider, the lattice parameters measurement, that spread may be more, but the crystal structure remains unaltered. And cold work material is in a relatively unstable state. So, therefore, it may have its reactivity may increase with the environment. So, therefore, its corrosion resistance of cold work material usually decreases, and in some material, because of the presence of residual stress, some material are susceptible to stress corrosion cracking. So, sometime therefore, the cold work material may not be used in the cold work condition in many cases, and they will be given a treatment which is called annealing treatment, or we will know about it little later. As against this hot work, cold working, hot working also there is a change in shape of the product, shape and size of the product, with little change in grain shape and morphology. There is absence of texture, but it also depends on the prior cold work. If you have given a material very heavy cold work, and then if you are doing hot working, their steam, it may be difficult to remove some of the texture. But usually by and large, effect of hot working is does not, the hot working does not lead to development of preferred orientation, and material property in polycrystalline material is isotropic. There is little change in dislocation density, because the entire operation is done at a high temperature, where dislocation mobility is higher. Secondly, dislocations annihilate, and there is a process of dislocation annihilation, we will know about it. So, there is a little change in dislocation density, there is no loss of ductility. In fact, when you are hot working a cast material, it in fact improves, where it removes segregation of cast metal and improves its ductility. There is no significant increase in strength, only apart from certain hot working processes we do, there is some amount of grain refining. So, there may be some amount of increase in strength, but by and large for most cases there is no significant increase in strength, and in the hot work material there is little residual stress or stored energy, and crystal structure it remains unaltered. Now, when you work, obviously the point that comes up, what are the variables that you can control, and these are listed here. So, when you apply a stress, so that means stress is at your disposal, you can control the stress that you apply, you can control the temperature at which you are working, you can control the amount of strain you want to give at every stage of deformation. At every stage, say suppose rolling is done in several stages, and in each pass how much strain you will give you can control. You can control the strain rate, the rate at which the deformation will be given, the rate at which you apply the load, that can be controlled, and obviously time is possibly you can consider this also as a variable. How much time you spend, say this time is also important. Sometime this hot working done in stages, and therefore, in two stage deformation there may be some amount of time gap between the two. So, there also time will play an important role, and although in an actual deformation process these variables may vary, particularly stress, strain rate may vary with time from point to point, but often we consider the material response. To understand the material response, we often assume that the deformation takes place under either constant stress or constant strain rate, to understand the underlying physical processes that take place during deformation. And let us see when we consider the material behavior under this condition, what do we get. So, when we are trying to deform a material, what we try is a change in shape. Say this is my initial size, we want to roll it down to this. So, that means with every step that strain that evolves in the material, and how does this strain or shape change evolve with time. And we can visualize, suppose we are doing this processing by applying stress to the material, and we know that deformation takes place only major deformation takes place through slip, and sometime twin also plays an important role. Let us say these are the slip plane, and when the slip takes place, through this process of slip, its shape changes from here to here. And since it is a polycrystal material, you have different grains, each grain will have a slip system, specific slip system, they will be differently oriented with respect to this axis. So, it is indeed a very complicated process, but nevertheless if we measure the stress, we may find that with time the stress the material can withstand varies like this. If I say we are applying the stress like this to a material, and let us see what is the behavior, how does the strain, I mean what is the strain response to this application of stress, and how does it evolve with time. This will clearly depend on temperature. If the temperature is low, say let us say it is around room temperature for steel, you will find initially the strain builds up, but after some time it is stagnant, strain does not increase. So, that means cold working always there is a limit how much strain that you can give, there is a. So, cold working you can give only limited strain. So, material hardens, and therefore, you cannot strain it further. To give a further deformation, you have to give intermediate, restore its initial structure, bring down its strength. So, give it an annealing treatment, then only you will be able to deform. But if you are deforming at a higher temperature, say it is something like hot working, but the temperature is still at the lower end, near the lower end of the hot working temperature. Here you will find there is a time dependent deformation, that is strain, it goes like this, and here what happens is initially there is some amount of strain hardening, but since the temperature is high, as the dislocation density, because of dislocation density deformation dislocation density goes up, but the temperature is high, dislocations have another mobility, that is it can climb, cage dislocation can climb and annihilate also. So, dislocation, that structure also recovers, which brings down the dislocation, and on the whole during the process of deformation there is a steady state. So, increase in dislocation density because of working is balanced by loss of dislocation due to a process called recovery or thermally activated movement of dislocation, and then you have a steady state, and this type of behavior allows you to give large deformation to the material. Now, alternatively, if you are increasing the temperature even higher, you go close to 0.9 Tm, then what happens? There will be the grains which gain deform, but simultaneously some of this, because the deformation is so large, simultaneously some of new grains start nucleating, and these are strain free grain, and this is called the process of recrystallization. So, during working, the cold work grain, as that is highly strained grain, they are replaced by strain free grain. These are strain free grain, and when such grains nucleate, its strength comes down also, and in fact, on the whole you may find that means you have an oscillating, that is strain evolution with a time, and you can say this is a pseudo steady state. This average line, you can say this is quasi steady state. situation. So, as against this that load control process, you can also visualize a strain control process, and where I think same thing here on this axis we write strain rate, and most of the cases what we control in the rolling or say wire drawing, we control the strain rate. That means, it is material is pulled at a constant strain rate. So, this is how you are applying the strain rate to the material. Then what happens to the stress? In the case of this, in the case of let us say in this particular case, the material strain hardens, it goes like this, and in fact this strain hardening can also be written as, let us say this is the stress is sigma 0 is the yield stress, beyond which there is a significant plastic deformation, and after this the plastic strain can be written as k epsilon to the power n. So, material hardens. So, unless you increase the load, you will not be able to maintain the same strain rate. To maintain same strain rate, you have to go on applying increase the pressure at which the apply increasing pressure to the job that you are shaping. Whereas, and this happens when you are doing the working at a lower temperature, room temperature. If you are working in this temperature range, say 0.5 Tm, in that case something like this happens. Initially this your load increases, but after some time a steady state is attained, and this is where the flow stress, this is called flow stress. So, material continues to flow at an at a fixed flow stress, and the flow stress does not change with time, and this is where you can give very large amount of deformations. And in the other case where the material behavior is such that in the deformed grain, that energy exceeds a critical energy, in that case if this is a deformed grain, this recrystallization starts. So, strain free grains nucleate at the grain boundary and they keep on growing, and when these strain free grains develop, their strength is low. So, suddenly you get this kind of an oscillating behavior, that flow stress keeps oscillating, and this is the average quasi static flow stress, quasi static flow stress. Now, we will see how, I mean what type of materials or where do you get this kind of behavior, where you get this type of behavior, and this type of behavior you get only in case of cold working. Now, hot working is a thermally activated process, and here what happens is when you deform, there is slip taking place, and for the slip to take place, the dislocation movement is necessary. Dislocations are generated, but when this process takes place at high temperature, as dislocations are generated, there is also another process, parallel process of dislocation annihilation, because dislocation gets some added movement here, dislocation can climb, and then by that they can rearrange themselves and try to occupy the minimum state of energy. So, this process, because of this thermally activated dislocation glide, so we can say that hot working, the primary mechanism is thermally activated dislocation glide, and this accompanied by there is recovery by dislocation annihilation. If there is a positive dislocation, there is a negative dislocation somewhere here. So, this will climb down, it comes here, it comes here on the same plane, and then it moves on this plane, and then actually it annihilates. When the two join together, if the two join together, the dislocation will disappear. And rearrangement of dislocation leads to the formation of subgrain, and we had seen it earlier. We will again see some examples. Now, this process of this dislocation glide is also affected by the stacking fault energy. We know that if material where the stacking fault energy is high stacking fault energy material, they can cross slip. If gamma stacking fault energy is high, stacking fault energy, if this is high, in that case cross slip takes place, and this leads to the formation of a nice well knit dislocation network. So, aluminum, ferritic steel, they are that type of material where stacking fault energy is high. So, here dislocation cross slip, and this type of strain softening is easier, recovery is easier, and a steady state here may be attained. So, here you will have this kind of flow stress behavior. Flow stress behavior will be something like this, whereas as against this austenitic steel and nickel. So, these are examples of materials of low stacking fault energy, and materials in low stacking fault energy you will often find twins in the structure. So, they are called in cold work and annealed structure you get twin. They are also signs, they also of low stacking fault energy. So, here the dislocations which split into partials, they cannot cross slip. The slip planes are very specific. So, it will be unable to cross slip, and such type of dislocation network or formation or boundary formation or dislocation grain boundary formation and recovery process will be more difficult. So, here with therefore, stored energy will increase in this particular case, and when the stored energy reaches a critical value, when it reaches, then recrystallization sets in. Recrystallization sets in, new strain free grains are formed, and these new grains too undergo deformation, and this process continues, and this gives oscillating flow stress, and this is called dynamic recrystallization. That means, recrystallization is taking place when the deformation is being given to the material. Now, what is a recovery process? We just said that a dislocation is a process of rearrangement of dislocation. If you recollect, this is the stress field of a dislocation. If you recollect, so this top part is subjected to compressive loading, the bottom half of the edge dislocation is subjected to tensile loading, and therefore, there is a stress field around it, and if there is another dislocation, it also has its own stress field. Now, here both this portion also is tensile, this is also tensile. So, it will be difficult to accommodate the two will repel each other, but what happens if it climbs up? We have seen that this 45-degree line, this is a 45-degree line. If it goes beyond this, then the force on the dislocation, instead of being one of repulsion, here it becomes one of attraction, it comes here, and once it reaches this particular point just above this here, somewhere just above this, this is a stable configuration, and here if it moves slightly this side, the force acts in this direction. If it is slightly displaced on this side, force acts on this side, brings it here. So, that means, if the process, if the temperature is high, the dislocation can climb, because the vacancy from somewhere in the lattice, they will diffuse to this place, and this dislocation will climb, and once it exceeds this crosses this particular line, then it comes because of this its stress field, this moves to this position of equilibrium, and in this way such an array of dislocation can form in a crystal, which is shown here in this lattice. And I think if you see on this, I think I have used some color here. So, here you can see on this if you can see on this screen, you will see better. And now, here so this is called a dislocation boundary, and when you have dislocation like this, we have seen that this has a Berger vector B, which is a displacement. If this is the distance between the two dislocation capital D, then the two, as if it's like a tilting, it's called a tilt boundary. This part of the crystal is rotated slightly through an angle theta, and this angle of tilt is given by B over capital D. And when this angle of tilt is around say 5 to 15 degree degree angle, this misorientation is 5 to 15 degree. So, we call this as a low angle boundary, low angle grain boundary or tilt boundary. Now, annihilation process is something like this. If you have this type of dislocation, this is a negative dislocation. If a vacancy moves from here, comes, this will climb down, it will finally come here, and in this, when they are both in the same plane, they move towards each other, and finally they will annihilate. So, this is a process of recovery, some rearrangement of dislocation and dislocation annihilation, the stored energy is minimized. Next let us see the process of recrystallization. We have just seen that as a result of deformation, say if this is the original structure, these are the different grain. If you deform it, grain shape changes, and when this shape changes, each of these boundary, they have some energy. So, it is the grain boundary energy also has increased. There is lot of dislocation density in the material, and bulk of this dislocation density will be here, and then therefore, the material is in a highly unstable state, and if there is if we heat the material or if we provide some amount of thermal activation, these worked grains, they are replaced by strain free grain, some strain free grain nucleates here, like what is shown here. This is a strain free grain, the nucleate, and these grains have a much lower strain. So, this cold work grain, this has high strength, that is strength is high, whereas these are recrystallized strain, his flow stress is low. Now, during the process of working, the plastic work that you do, that 90% of the work is dissipated as heat. There may be some amount of adiabatic heating, the job may get heated up, and but only 10% of this energy is stored in the form of either increased dislocation density or increased grain boundary energy. So, there is so that elastic it is stored some form of stored energy in the material, and this cold work structure is thermodynamically unstable. And in fact, what you can see here, it is possible that when this strain free this cold work grain is replaced by the strain free grains. So, these are the strain free grain. So, new surface is being created, this has also some energy, and we have seen that if this energy is say suppose we assume these are spherical, its energy will be 4 pi r square, and its surface energy if we say is a gamma. So, this is positive, this much of energy has to be supplied, and this is provided by the elastic stored energy, that is delta G V. This is the elastic stored energy per unit volume, and if you multiply this by the volume, you get the total energy. Now, you can also you can differentiate it. So, this is a function of R. If you differentiate this delta G with R, equate it to 0, you can find out a critical size of the nucleus, and also you can find out what is the maximum, that is that activation hill which it has to exceed, so that the process continues, and this is shown in this figure over here. So, the critical nucleus size and the activation energy, this is the total energy, and you differentiate it, equate it to 0. Here I think sigma represents the surface energy, and this is the critical nucleus size. So, in fact, this is negative. So, therefore, this will be positive, the critical nucleus size is positive, and this is the activation hill, which is shown in this diagram. This is the delta G plotted against R. This is the activation hill, and this is the critical nucleus size. Now, as cold work increases, what happens? As cold work increases, that activation hill, what will happen to the activation hill? Obviously, if you increase the cold work, you can imagine like this. You have a cold work material, you have somewhere here annealed material, it is a more stable material, that state is here. Now, from here, although there is a driving force, it does not, process does not continue all by itself, it has to go through, you have to provide a thermal activation, and this is the thermal activation. This is that delta G star. So, this is the delta G star. Now, if you have the more cold work, what happens? You can see from this diagram here, this is a previous expression, this activation hill decreases. So, that means, if you have more cold work, then the activation hill decreases, also the critical nucleus size also decreases. So, that means, if you have increased cold work, so this will be like this. You increase the cold work further. So, that means, this is the critical nucleus size. So, you increase the cold work, the activation hill comes down, the critical nucleus size comes down. So, therefore, if you want to get a finer structure, you have to give higher amount of cold work, and if you want to have a very coarse grain structure, then you have to give very little cold work to the material. Now, this process of this is the energetics of you can say this is the we have just considered the energetics of recrystallization process, that is the thermodynamics of the recrystallization process. If you look at this slide here, apart from this, we have just considered what is called the thermodynamic instability, and once the stable nucleus develop, they will grow also, and this process of growth also is also important, and this nucleation rate we know that the rate of nucleation will depend on that activation hill. If this activation hill is low, nucleation rate will be very high, that means faster nucleation, higher cold work, higher is the nucleation rate, and in fact and this is the activation energy. So, basically when you look at this delta G, any thermal any free energy, it has two components, one is that enthalpy part and this is the entropy part, and when you split the two, you know that there is a pre exponent term, this is delta G by R T, this becomes delta H by R T minus delta S by R. So, this does not depend on temperature, only this part is the temperature dependent, and this is called the activation energy of recrystallization. So, this is what is shown over here. Now, apart from this, there will be a growth process also, and which is pictorially shown here. When this number of nuclei they form, they will grow also, and when they grow, there will be a factor called impingement factor, which is shown here. If this grows, if this grow, finally a stage will come when they will touch each other, and when they touch, the growth will decrease. When these recrystallized grain they touch each other, because of that impingement factor, the rate of growth will slow down. So, therefore, the process of recrystallization, if you can say that F is the fraction recrystallized. So, here it is 0 and here it is 1. Then we say that fraction recrystallized, it follows something, a plot something like this. This is 1 minus exponential minus some constant time to the power n, and nature of this is like this S plot. So, somewhere in between you have the maximum rate of transformation, where both nucleation and growth they are both favorable, they add up and you have maximum, and later on the growth actually again becomes slower, and nucleation also will become more difficult, because most of the sites have where the nucleation could take place, the grains have nucleated. So, therefore, again the rate decreases, and this is most of these types of solid state transformation, they follow this kind of kinetics, and we will be referring to this type of equation again and again. Now, what happens to some of the properties which is shown over here? Now, with annealing, see, this is plot, this represent the strength. So, strength initially with annealing temperature, it does not decrease much, initially there is marginal decrease, and this is the stage where it is a maximum decrease, and then later on also this tapers off, rate of decrease goes down. Whereas, internal strain or internal stored energy, this decreases significantly in this part, in this region, this temperature zone. Whereas, the grain size you will find over here, you have very fine grain, but if you still raise this annealing temperature, you will find when you raise beyond a temperature, these grains keep growing and they can even become very large. So, what it means that annealing, you can divide the process of annealing into 3 distinct stages, and which are shown here in this diagram. Here this is called, this stage is called the recovery zone, or recovery stage. This is the recrystallization stage, and this is the grain growth stage. And accordingly, this all several other physical properties also will change. Say suppose ductility here will be low, the ductility here there may be marginal change, but here the ductility will increase, and again the ductility may decrease. If the grains becomes coarser, then the material becomes less ductile, something like this. So, if you sum up that process of recrystallization, we have seen that some amount of cold work is necessary for recrystallization to take place. the lower the degree of cold work, higher is the recrystallization temperature. That means, lower cold work you have to give more amount of thermal activation, because delta less cold work means this is low, delta G V is low, there is activation hill is high. Then annealing time also decreases decreases recrystallization temperature. If you increase it, if you hold time increase, then also recrystallization temperature decreases, but temperature effect is much more. Temperature effect is exponential, whereas time effect you can see that time effect is much less than the temperature effect. Temperature is exponential, whereas time effect you have seen that is T to the power n is a fraction, it is a very small compared to the temperature effect. Alloy addition, if you add alloy addition, then the material becomes stronger, its recrystallization temperature goes up. Then larger original grain size, if the grain size is very large, then whenever you cold work, the grain boundary of course increases, but if you have a finer grain boundary area increase will be much more. So, here, so therefore, if the original grain size is higher, then the recrystallization temperature is also high, and larger original grain size, then the higher cold work is required to get recrystallization at the same temperature, recrystallization temperature. Now, let us look at why does grains grow. Now, grain boundary they have certain energy, and most of the cases you will find the grain boundaries are like this. So, this angle in 2D it will be something like 120 degree. So, this if you resolve this grain boundary they have certain energy, they are like tension, and if they are all same you can show that if they are at 120 degree the total force on this point will be 0 and they will be stable, and which is shown over here. These are 3 grains, these are the grain boundary energy. Now, if you assume that all are same, all are equal to gamma, then you can easily show as over here this type of force balance is possible, and in that case all 3 angle, if they are all equal, then all theta 1, theta 2, theta 3 will be equal. So, therefore, 3 lines can meet with equal angle, and that angle is 120, obviously 120 degree. Now, what happens? How do you estimate? The grain boundary has an energy, but is it possible to estimate the grain boundary energy? Yes, it is. One of the simplest way is if you take a polished material, it's a polished material has been taken, it has mirror finish, you heat it in vacuum, then what happens? This grain boundary they get etched, and when you look under microscope and there are profilometer, you can follow the profile, you will find that grain boundary area there is a dip something like this, and here you can take a section and draw a line and measure this angle of that angle between the 2 grain, or else in a profilometer reading also it is possible to measure this angle. And if you do this, so this is the surface energy between solid and vapor. You can say this is the any solid, there will be some amount of vapor, we can thermodynamically, howsoever less may be the vapor pressure, there may be some amount of vapor in the environment surrounding it, and there is a stable equilibrium. So, therefore, what you can see here, equating the force, you can resolve it in this here. So, the vertical component will be gamma S V cos theta by 2, there will be 2 of these. So, this is the upward force twice gamma S V cos theta by 2, and this will be equal to this surface energy along this direction. And in reality it is possible to calculate this also. It is possible to calculate this from a simple concept that on the free surface some of these bonds are missing. So, here what you can say, this atom, so every atom has 4 bonds. So, this atom near the surface one bond is missing. So, that means if we say that bond energy is epsilon, then the missing energy per atom is epsilon by 2. So, and this epsilon it is possible to calculate from the latent heat of vaporization, and this latent heat of vaporization it is possible to calculate, and this is how the grain boundary energies have been calculated, and it is found that always this grain boundary latent heat of vaporization is greater than latent heat of fusion, and it is much greater than sorry, this is solid to vapor, this is much greater than latent heat of fusion, and this is from liquid to vapor, latent heat of vaporization, liquid to vapor, this is latent heat of sublimation from solid to vapor, and always this is the highest. Next is latent heat of vaporization. Difference between these two is not much, but they are both of these are significantly larger than latent heat of fusion. So, even though, so that means what it indicates that this grain boundary energy will definitely be much smaller than this energy, that means this is gamma S V will be much smaller than this grain boundary energy. So, maybe 0.3 times or even less, but it has a definite value. So, what it means, if you have such a tension, surface tension or grain boundary energy existing, then it is possible to show easily that there will be instability of the curved grains will be unstable, there will be a force acting this side. So, any curved grain will try to straighten out, and the force you can easily show this, that this force acting on this grain boundary will be equal to proportional to grain boundary surface tension gamma L over R. So, only when R is flat, that means something like this, force acting on it is 0, otherwise there will be some force. So, therefore, wherever you have curved boundary like this, so they will try to straighten, and in fact, this will move towards this, and finally, this straight grain will form and this grain will get eliminated. Similarly, here also. So, that means any curved boundary will be unstable, and they will try to straighten up, and it is possible to show that rate at which this, therefore, the grain will grow will be determined by the surface energy, and this is gamma over R. R you can say it is half the grain size. So, that means this is d by 2. So, in a way you can say the rate at which the grain growth takes place is inversely proportional to the grain size. Then you can easily show that grain growth kinetics will be something like this, d square minus d 0 square is equal to k T. In general, it has been found that this exponent, this is written as 1 over n. So, instead to get 2, n has to be 0.5, but for most material this may be around 0.2 to 0.3, it is not exactly 0.5. Now, deformation, as we have seen deformation, and earlier if I try to recollect that the tensile axis tend to rotate towards the slip direction, then compressive axis also moves. So, that means that slip plane normal tends to move to the compressive axis. So, therefore, in a polycrystalline materials, in the single crystal this is possible, polycrystalline there is a lot of restrictions, the grains cannot rotate and move freely, they will get distorted, fragmented, but nevertheless there will be some effect of rotation and you get a texture. This is a cold works texture, and which will be, so therefore, there will be a preferred orientation which is called cold works texture. Likewise, you can also have annealing texture if cold work amount is extremely high, is a greater than a critical value, then even if you anneal, there will be some amount of texture, and this texture also depends on type of second phase particle that are present in the material. Like in steel, if you have aluminum nitride, this favors this gives a texture which is quite favorable for deep drawing kind of steel. So, if you are deep drawing, you want a preferred orientation, that means in case of a deep drawing, through thickness strength you want very high. So, you want such a texture, so that the thickness does not reduce, but on the planar it should reduce very easily. So, that type of texture it is possible to develop through by controlling cold work and annealing, and by the presence of certain inclusions like aluminum nitride and steel. So, with this we finish this topic, and what we have looked at, we looked at the process of annealing, the variables that control annealing, we looked at that recrystallization temperature, factors that determine recrystallization temperature, we looked at mechanisms of annealing, grain growth, origin of texture. Thank you very much.